What if I told you that everything you've ever seen, every star, every galaxy, every shimmering nebula in the most powerful telescope images, represents less than 5% of what actually exists in the universe? Right now, as you're watching this, you're surrounded by an invisible ocean of matter and energy that outweighs all the visible stuff by a factor of 20 to 1. And here's the part that should genuinely terrify and excite you. We have absolutely no idea what most of it is. I'm not talking about things that are just really far away or too dim to see. I'm talking about fundamental components of reality that don't interact with light at all. They don't emit it. They don't absorb it. They don't reflect it. They're invisible in principle, not just in practice. And yet, without these invisible components, you wouldn't exist. The galaxies wouldn't have formed. Stars wouldn't have ignited. The universe as we know it would be impossible. Here's what will blow your mind. The matter that makes up your body, the Earth, the Sun, and everything you can see with the most powerful instruments is considered abnormal in cosmic terms. You are made of the weird stuff, the rare stuff, the exotic minority. The universe is overwhelmingly composed of things we cannot see, cannot touch, and barely understand. And we're going to spend the next 3.5 hours exploring why that is, what it means, and how it changes everything you thought you knew about reality. Before we dive into this invisible cosmos, if you're ready to have your understanding of reality fundamentally restructured, hit that like button and subscribe. This is going to be a journey, and I want you along for the ride. Also, drop a comment telling me where you're watching from and what time it is for you right now. I'm curious how many different parts of the world are about to discover the invisible universe together. Are you watching during your morning coffee in Brazil? Late night curiosity session in Tokyo? Let me know, because we're all inhabitants of this mostly invisible cosmos, and I want to know who's waking up to that fact right now. Let's start with something simple. Light. You think you understand light, right? It's what lets you see things. But here's the first twist in our journey. Light is incredibly limited. The light your eyes can detect represents an absurdly narrow slice of the electromagnetic spectrum. If the entire electromagnetic spectrum were stretched across a football field, the visible light portion would be about the width of a single blade of grass. Think of it like this. Imagine you're trying to understand an enormous symphony orchestra, but you can only hear one specific note from one specific instrument. That's essentially what our eyes do with reality. We're experiencing a tiny, almost arbitrary slice of what's actually out there. Now, you might be thinking, okay, but we have instruments. We have radio telescopes, infrared cameras, X-ray detectors. We can see beyond visible light. And you'd be absolutely right. When astronomers started looking at the universe in different wavelengths, they discovered entirely new phenomena. Radio galaxies that are invisible to optical telescopes. Infrared bright galaxies hidden behind dust. X-ray emitting black holes. The universe revealed itself to be far richer and stranger than visible light alone suggested. But here's where things get truly bizarre. Even when we observe the universe across the entire electromagnetic spectrum radio waves to gamma rays, we're still only seeing that same 5% of reality. All forms of electromagnetic radiation, from the longest radio waves to the most energetic gamma rays, only interact with normal matter. And normal matter, as we're about to discover, is the minority component of the universe. This raises an obvious question. How do we know there's something else out there if we can't see it? How did scientists discover that 95% of the universe is invisible? The answer involves one of the most elegant pieces of detective work in the history of science. And it started with a Swiss astronomer named Fritz Zwicky in 1933. Zwicky was studying something called the Coma Cluster, a massive collection of over 1,000 galaxies located about 300 million light years from Earth. He was measuring how fast these galaxies were moving within the cluster, and something didn't make sense. The galaxies were moving way too fast. Think of the cluster like a swarm of bees. If the bees are moving too quickly, they should fly apart. The gravitational attraction between them wouldn't be strong enough to hold them together. Zwicky calculated the mass of all the visible matter in the Coma cluster, all the stars, all the gas, everything he could see, and it wasn't nearly enough gravity to keep those galaxies bound together at the speeds they were moving. His solution: there must be matter we can't see. Lots of it. In fact, he calculated that there must be about 400 times more invisible matter than visible matter in the Coma cluster. He called this invisible stuff dunkel mattery dark matter. And here's what's remarkable. He was essentially correct. His numbers were off, but the fundamental insight was right. Most of the universe is invisible. Now, here's what you need to understand. Zwicky's discovery was largely ignored for decades. The scientific community wasn't ready for such a radical idea. It seemed more likely that there was an error in the calculations, or that our understanding of gravity needed minor adjustments, rather than accepting that most of the universe was invisible. This is a pattern we'll see repeatedly. Reality often exceeds our imagination, and we resist the most radical explanations even when they fit the evidence best. Let me give you an analogy that might help. Imagine you're watching a puppet show, but you can only see the puppets, not the strings or the puppeteers. The puppets are moving in complex, coordinated ways. You could try to explain their movements by assuming they're somehow propelling themselves, or that there are invisible forces between the puppets. But the simplest explanation is that there's something you can't see, the strings and puppeteers controlling everything. Dark matter is like those invisible puppeteers. We can see the effects, the movements of galaxies and clusters, but not the cause itself. The breakthrough that made dark matter impossible to ignore came in the 1970s, thanks to an astronomer named Vera Rubin. Rubin was studying the rotation of spiral galaxies, and she discovered something that shouldn't be possible according to the laws of physics as they were understood. When she measured how fast stars were orbiting around the centers of galaxies, she found that stars on the outer edges were moving just as fast as stars closer to the center. This is completely wrong according to Newtonian physics. Think about the solar system. Mercury, the closest planet to the Sun, orbits much faster than Neptune, which is far from the Sun. This is because there's more mass inside Mercury's orbit, providing more gravitational pull. The farther out you go, the slower things should orbit. This is basic Kepler, basic Newton, stuff we've understood for centuries. But galaxies don't work that way. Their rotation curves are flat. Stars at the edge move just as fast as stars near the middle. It's as if Neptune were orbiting at the same speed as Mercury. The only way this makes sense is if there's a massive halo of invisible matter surrounding each galaxy, extending far beyond the visible disk. This dark matter halo contains most of the galaxy's mass and provides the gravitational pull needed to explain those flat rotation curves. Here's what will blow your mind about this. Rubin measured dozens of galaxies, then hundreds. Every single spiral galaxy she looked at showed the same pattern. This wasn't an anomaly or an error. This was a fundamental feature of the universe. Every galaxy we've ever studied is embedded in a massive halo of invisible matter that outweighs all the visible matter by about 6 to 1. Think about what this means for a moment. When you look at a beautiful image of a spiral galaxy, the Andromeda Galaxy, for instance, or the Whirlpool Galaxy, what you're seeing is just the glowing tip of an enormous invisible iceberg. The visible spiral is a relatively small, luminous tracer floating in an ocean of dark matter. The galaxy you see is not the real galaxy. It's just the part of the galaxy that happens to emit light. And it gets stranger. Computer simulations of how galaxies form show that without dark matter, galaxies wouldn't exist at all. In the early universe, normal matter was too hot, too diffuse, too affected by radiation pressure to collapse into the dense clumps needed to form galaxies. But dark matter doesn't interact with radiation. It doesn't feel radiation pressure. So dark matter collapsed first, creating gravitational wells Think of them as invisible valleys into which normal matter could fall. The dark matter provided the scaffolding, the invisible framework upon which all visible structure in the universe was built. You exist because of dark matter. The Milky Way galaxy exists because of dark matter. The solar system, the Earth, life itself, all of it depends on these invisible structures that formed in the early universe. We are, in a very real sense, living inside an invisible cosmic architecture that we're only now beginning to map. Now, before we go further, let me address the obvious question you're probably asking. What is dark matter? What is this stuff that makes up 85% of all matter in the universe? And here's the frustrating answer. We don't really know. We have some ideas, some candidates, but no confirmed detection. Let me give you a sense of what we do know, and more importantly, what we don't. First, what dark matter isn't. It's not just regular matter that happens to be dark. It's not planets or black holes or brown dwarfs or dust. We can rule all of that out based on various observations and measurements. Regular matter, the stuff made of protons, neutrons, and electrons, is called baryonic matter by physicists. And we can calculate exactly how much baryonic matter exists in the universe based on observations of the cosmic microwave background and the abundance of light elements formed in the Big Bang. The math is clear. There isn't enough baryonic matter to account for the gravitational effects we observe. Dark matter must be something else entirely. Something non-baryonic. Something outside the standard model of particle physics. The leading candidate is something called WIMP's weakly interacting massive particles. The idea is that dark matter is made of particles that have mass, which means they have gravity, but don't interact with electromagnetic radiation, which means they don't emit, absorb, or scatter light. They might interact via the weak nuclear force, which is why they're called weakly interacting. These particles would be passing through you, right now billions of them streaming through your body every second. And you'd never notice because they barely interact with normal matter at all. Scientists have built incredibly sensitive detectors deep underground, shielded from cosmic rays and other interference, hoping to catch the rare occasions when a dark matter particle might collide with a normal atom. These experiments have names like Xenon, Lux, and Super CDMS. They've been running for years, getting more and more sensitive, and so far, nothing. No confirmed detection. Dark matter remains stubbornly invisible and elusive. There are alternative candidates too. Axion's hypothetical particles billions of times lighter than electrons. Sterile neutrinos' ghostly particles that interact even less than regular neutrinos. Primordial black holes formed in the first fraction of a second after the Big Bang. Each has its proponents and its problems. The truth is, we're searching for something we've never seen, don't fully understand, and can only detect through its gravitational influence. And yet, we know it's there. The evidence is overwhelming. Galaxy rotation curves, gravitational lensing, the cosmic microwave background, the large-scale structure of the universe, all of it points to the same conclusion. 27% of the universe is made of dark matter. It's not a theory in crisis. It's a theory desperately searching for its missing piece. But here's where our story takes an even more shocking turn. Dark matter, mysterious as it is, isn't even the biggest component of the invisible universe. There's something else out there, something even stranger, something that makes up 68% of everything that exists. And unlike dark matter, which at least behaves in ways we can understand, it clumps together, it has gravity, it helps form structures. This other thing defies all intuition. It's not just invisible, it's actively pushing the universe apart. We call it dark energy, and it might be the strangest thing we've ever discovered. Stay with me, because we're about to explore the force that's determining the ultimate fate of everything that exists. Before we dive into the mystery of dark energy, let me explain what happened in 1998 that completely upended our understanding of the universe. Two teams of astronomers, the Supernova Cosmology Project, led by Saul Perlmutter, And the High-Z supernova search team, led by Brian Schmidt and Adam Rees, were trying to measure how much the expansion of the universe was slowing down. Let me back up and give you context. Since Edwin Hubble's discovery in 1929 that the universe is expanding, scientists assumed that gravity must be gradually slowing down that expansion. Think of it like throwing a ball up in the air. Gravity pulls it back down, slowing its ascent. Similarly, the gravitational attraction between all the matter in the universe should be acting as a brake on cosmic expansion. The question was, how strong is that brake? Will the universe eventually stop expanding and collapse back on itself? Or will it expand forever, just gradually slowing down? To answer this question, both teams were observing Type Ia supernova in distant galaxies. These supernova are incredibly useful because they're standard candles. We know how bright they actually are. So by measuring how bright they appear from Earth, we can calculate exactly how far away they are. By comparing the distance to these supernova with their redshift, how much their light has been stretched by cosmic expansion, the teams could measure the expansion rate at different points in cosmic history. Both teams expected to measure a deceleration, a slowing down of the expansion. What they found instead was acceleration. The universe isn't just expanding, it's expanding faster and faster. The expansion is speeding up. Let me emphasize how shocking this was. Imagine you throw a ball up in the air, and instead of slowing down as it rises, it starts accelerating upward, moving faster and faster. That's essentially what these astronomers discovered about the universe. It violates every intuition, every expectation. Something is pushing the universe apart, overwhelming the attractive force of gravity. And whatever that something is, it's incredibly powerful. It makes up 68% of the total energy density of the universe. The discovery was so unexpected that both teams initially thought they'd made an error. They spent months checking their data, looking for mistakes, considering alternative explanations. But the signal was robust. The universe is accelerating. In 2011, Perlmutter, Schmidt, and Rees were awarded the Nobel Prize in Physics for this discovery. And we still don't know what's causing it. Scientists call it dark energy, but that's really just a placeholder name, meaning the unknown stuff causing cosmic acceleration. We don't know what it is, where it comes from, or why it exists. We just know it's there, and it's dominant. Think about that. 68% of the universe is made of something we cannot see, cannot directly detect, and don't understand. Dark matter is mysterious, but dark energy is in a category of weirdness all its own. Here's one of the leading ideas about what dark energy might be. It could be a property of space itself. Einstein's equations of general relativity include a term called the cosmological constant, essentially, a number representing the energy density of empty space. Einstein originally introduced this term to make the universe static, then abandoned it when Hubble discovered cosmic expansion, calling it his biggest blunder. But it turns out empty space might actually have a small, positive energy density. And as the universe expands, creating more space, you get more dark energy. It's energy that comes from space itself. Think of it like this. Imagine a spring. When you stretch it, you're adding potential energy to the spring. Similarly, space itself might have an inherent energy, and as space expands, the total amount of that energy increases. Normal matter and dark matter get diluted. As the universe expands, spread the same amount of stuff over a larger volume, and the density goes down. But dark energy doesn't get diluted. Its density stays constant. So as the universe grows, dark energy becomes more and more dominant compared to matter. Now, here's where it gets really mind-bending. If dark energy is the cosmological constant, the energy of empty space, we can calculate what its value should be based on quantum field theory. When physicists do this calculation, they get an answer. And then they compare it to the observed value, the actual amount of dark energy we measure in the universe. The predicted value is bigger than the observed value by a factor of 10 to the power of 120. That's a 1 followed by 120 zeros. It's not just wrong. It's the worst prediction in the history of physics. This is called the cosmological constant problem, and it's one of the deepest mysteries in science. Why is the energy of empty space so much smaller than quantum field theory predicts? And yet, why isn't it zero? Why does it have this specific, small, but non-zero value that's causing the universe to accelerate? Some scientists think the answer might involve the anthropic principle, the idea that the universe must have properties that allow for the existence of observers, because otherwise there'd be no one to observe it. If dark energy were much larger, the universe would have expanded so fast that galaxies could never form. If it were negative, the universe would have collapsed long ago. Only in a narrow range of values can you get a universe where stars and galaxies and planets and life can exist. Maybe we observe the value we do because it's one of the few values compatible with our existence. But other scientists find this explanation unsatisfying. It feels like giving up, like saying, it is what it is, because if it weren't, we wouldn't be here to ask. There must be a deeper explanation, a mechanism that sets the value of dark energy. But so far, we don't have one. There are alternative theories too. Maybe dark energy isn't constant. Maybe it's a dynamic field that changes over time, sometimes called quintessence. Maybe it's a sign that our understanding of gravity is wrong on cosmic scales, and we need to modify Einstein's equations. Maybe we're living in a multiverse, and different regions have different values of dark energy, and we happen to live in a region where it's just right for life. The truth is, we don't know, and that's okay. That's what makes this exciting. We're living in an era where the fundamental nature of the universe is up for grabs. The standard model of cosmology lambda CDM, which includes dark energy as the cosmological constant and cold dark matter, fits the data remarkably well. But it requires us to accept that 95% of the universe is made of things we don't understand. That's either a massive failure of our current theories or a profound statement about how strange reality actually is. Let me give you a sense of what the universe actually looks like in terms of its composition. 5% ordinary matter atoms, the stuff you and I and the stars are made of. 27% dark matter invisible, non-baryonic particles that clump together and provide the gravitational scaffolding for structure. 68% dark energy, a mysterious component causing the universe to accelerate. But even that 5% of ordinary matter, most of it is invisible too. About 10% of ordinary matter is locked up in stars. The rest is floating between galaxies as hot, diffuse gas, or hiding in planets, asteroids, and other dark objects. When you look at the night sky, you're seeing an incredibly biased sample of reality. You're seeing the rare, glowing bits. The vast majority of even normal matter is dark. Here's an analogy that might help you visualize the invisible universe. Imagine the cosmos as an enormous city at night, viewed from space. The city lights, bright, visible, obvious, represent the stars and galaxies we can see. They're prominent. They catch your attention. They seem like the main event. But most of the city's mass isn't in the lights. It's in the buildings, the roads, the infrastructure, mostly dark, mostly invisible from above. That's dark matter. And surrounding the entire city, invisible and intangible, is the atmosphere, pressing down on everything, determining how the whole system behaves. That's dark energy. We're living in a dark universe, lit by rare exceptions. And we're trying to understand the whole city by studying only the streetlights. Now, you might be wondering, if we can't see dark matter or dark energy, how do we study them? What techniques do astronomers use to map the invisible? This is where things get really clever, really elegant. Because while we can't see these components directly, they do interact with the universe in detectable ways. They leave fingerprints, signatures, evidence of their presence. And scientists have developed some ingenious methods to read those signatures. One of the most powerful techniques is called gravitational lensing. Einstein's general relativity predicts that mass bends space, and light traveling through bent space follows curved paths. So when light from a distant galaxy passes near a massive object like a galaxy cluster, the light gets bent and distorted, like light passing through a warped lens. By studying these distortions, astronomers can map the distribution of mass in the cluster, including the dark matter. In 2006, astronomers studying a system called the Bullet Cluster provided some of the most direct evidence for dark matter using gravitational lensing. The Bullet Cluster is actually two galaxy clusters that collided and passed through each other. When they collided, the hot gas in each cluster, which makes up most of the normal matter, interacted, slowed down, and got left behind in the middle. But the dark matter doesn't interact with itself much, so the dark matter halos passed right through each other and kept going. Using gravitational lensing, astronomers could map where the mass actually was in this system. And what they found was beautiful and definitive. The mass was not where the visible matter was. The mass was with the galaxies in two separate clumps on either side of the collision site, exactly where the dark matter should be. The visible hot gas, most of the normal matter, was in the middle, but that's not where the gravitational lensing signal was strongest. The invisible dark matter had separated from the visible matter, proving that dark matter is real, substantial, and separate from normal matter. This is smoking gun evidence. It's incredibly hard to explain the Bullet Cluster without dark matter. Alternative theories of gravity, which try to explain galactic rotation curves by modifying gravity instead of invoking dark matter, struggle to explain this observation. The Bullet Cluster shows that the gravitational mass and a visible mass are in different places. That's only possible if most of the mass is invisible. Another technique for studying the invisible universe is the cosmic microwave background, CMB. This is the afterglow of the Big Bang, the oldest light in the universe, released about 380,000 years after the universe began, when it cooled enough for atoms to form. The CMB fills the entire sky, and it's remarkably uniform, about the same temperature in every direction, but not perfectly uniform. There are tiny fluctuations, hot spots and cold spots, differing in temperature by only 1 part in 100,000. These tiny fluctuations are incredibly important. They're the seeds of all structure in the universe. Regions that were slightly denser than average eventually collapsed under their own gravity to form galaxies and clusters. Regions that were slightly less dense became voids. The pattern of these fluctuations, their size, their distribution, their statistical properties, contains a wealth of information about the universe. And here's the remarkable thing. The pattern we observe can only be explained if the universe contains dark matter and dark energy in approximately the amounts I mentioned. The size of the fluctuations, the scale of the largest hot and cold spots, the overall structure, all of it matches predictions based on a universe that's 5% atoms, 27% dark matter, and 68% dark energy. Change those ratios, and the CMB pattern doesn't match observations. Missions like NASA's Wilkinson Microwave Anisotropy Probe, WMAP, and the European Space Agency's Planck satellite have mapped the CMB with exquisite precision. These missions have given us a baby picture of the universe, showing what it looked like when it was only 380,000 years old. And encoded in that picture is clear evidence for dark matter and dark energy. The invisible universe has left its signature on the oldest light we can see. There's also the large-scale structure of the universe, the distribution of galaxies across billions of light years. Galaxies aren't randomly scattered through space. They're organized into an enormous cosmic web, with dense filaments and clusters connected by thin bridges surrounding vast empty voids. This structure formed as gravity amplified the tiny density fluctuations from the early universe. Dark matter collapsed first, and galaxies formed where the dark matter was densest. Surveys like the Sloan Digital Sky Survey have mapped millions of galaxies and their positions in three-dimensional space. The pattern they've revealed, the cosmic web, matches computer simulations of structure formation in a dark matter universe. The simulations and observations agree remarkably well. Without dark matter, you can't get the large-scale structure we observe. The universe would look completely different. So we have multiple independent lines of evidence for the invisible universe. Galaxy rotation curves, cluster dynamics, gravitational lensing, the cosmic microwave background, large-scale structure, and the accelerating expansion. Each technique probes the universe in a different way, yet they all point to the same conclusion. The universe is mostly invisible, composed primarily of dark matter and dark energy. Here's what should genuinely blow your mind. All of this evidence comes from different epochs of cosmic history, from different physical processes, using different observational techniques, and it all converges on the same picture. The early universe, as revealed by the CMB, requires dark matter and dark energy. The formation of structure over billions of years requires dark matter. The current dynamics of galaxies and clusters require dark matter. The acceleration of the expansion requires dark energy. It's a consistent story, stretching from the first moments after the Big Bang to the present day. This kind of convergent evidence is powerful. In science, when multiple independent approaches all point to the same conclusion, that conclusion becomes very hard to dismiss. Maybe any single line of evidence could be explained away. Maybe there's some alternative explanation for galaxy rotation curves, or some exotic form of normal matter hiding in clusters. But explaining all the evidence without invoking dark matter and dark energy? That's extraordinarily difficult. And yet, we still don't know what dark matter and dark energy actually are. We have overwhelming evidence that they exist, but their fundamental nature remains mysterious. It's like being absolutely certain that something is in the room with you. You can feel its presence, see its effects, map its location, but when you turn on the lights, there's nothing there. The invisible universe is real, substantial, and dominant, but it refuses to reveal itself directly. Now, if you're still with me, take a moment to appreciate what we've covered. We've gone from the discovery that galaxies are embedded in dark matter halos to the revelation that the universe is accelerating under the influence of dark energy. We've explored multiple lines of evidence, from gravitational lensing to the cosmic microwave background. And we've confronted the humbling fact that we only understand 5% of what exists. If you're finding this as mind-blowing as I am, hit that subscribe button. We're going to go even deeper, exploring what the invisible universe means for the fate of the cosmos, for the nature of reality, and ultimately, for you personally. Drop a comment letting me know what's blowing your mind most so far. Is it dark matter? Dark energy? The sheer scale of what we don't know? I read every comment, and I'm genuinely curious what's resonating with you. Let's talk about what the invisible universe means for the future, the ultimate fate of everything that exists. Because dark energy isn't just some abstract curiosity. It's determining how this story ends. And the ending is both more beautiful and more terrifying than you might imagine. For most of human history, when people thought about eternity, they imagined a static universe, unchanging and everlasting. Then, in the 20th century, we discovered the universe had a beginning, the Big Bang, and that it's been evolving ever since. The next question was obvious. How will it end? Before the discovery of dark energy, there were a few possible scenarios. If the universe contained enough matter, gravity would eventually overcome the expansion, and the universe would collapse back on itself in a big crunch, the opposite of the Big Bang. All the galaxies would rush together, space would contract, temperatures would soar, and eventually everything would be crushed into an infinitely hot, infinitely dense point. The universe would end in fire. Alternatively, if there wasn't enough matter to halt the expansion, the universe would expand forever, gradually cooling as it grew. Stars would burn out, galaxies would fade, and eventually the universe would become a cold, dark, empty place. This scenario was called the Big Chill or heat death, the universe would end in ice, not fire, a long, slow fade to darkness. The discovery of dark energy changed everything. Not only is the universe expanding, but the expansion is accelerating. And if dark energy remains constant, if it's truly the cosmological constant, then the acceleration will continue forever. The ultimate fate of the universe is something even stranger than the Big Crunch or the Big Chill. It's called the Big Rip. Here's how it works. Right now, dark energy is dominant on the largest scales. It's driving the expansion of space on scales of hundreds of millions of light years. But it's not yet dominant on smaller scales. Galaxy clusters are still held together by gravity. Galaxies are still stable. The solar system is still intact. You're still held together by electromagnetic forces. But as the universe continues to accelerate, dark energy will become increasingly dominant on ever smaller scales. Eventually, we're talking trillions of years in the future. The acceleration will become so strong that it will overcome the gravitational binding of galaxy clusters. Clusters will be torn apart, galaxies flying away from each other faster than light. Then, individual galaxies will be disrupted. The Milky Way will be shredded, stars flung into intergalactic space. Then solar systems will be torn apart, planets ripped from their orbits. Then planets themselves will disintegrate. Then molecules, then atoms, and finally even atomic nuclei will be torn apart by the accelerating expansion of space. This is the Big Rip scenario, where the universe literally tears itself apart at every level. It's like being caught in a cosmic explosion that never stops, that keeps getting stronger, that eventually disrupts every bound structure in existence. The good news, if you can call it that, is that this won't happen for an unimaginably long time. We're talking tens of billions of years, possibly much longer. But if dark energy is constant and the acceleration continues, this is the ultimate fate awaiting the universe. Now, there's a huge if in that scenario. If dark energy is the cosmological constant, then yes, the Big Rip is a possibility. But we don't actually know if dark energy is constant. Maybe it's changing over time. Maybe it will weaken in the future, or strengthen, or even reverse. Different assumptions about dark energy lead to different cosmic futures. This is one reason why understanding dark energy is so important. It's not just about satisfying curiosity. It's about knowing the ultimate fate of everything. Let me give you another scenario, one that's perhaps even more disturbing in its implications. Some physicists have proposed that the vacuum state of our universe, the ground state of all the quantum fields that permeate space, might not actually be the lowest possible energy state. It might be a false vacuum, temporarily stable, but not truly stable. If that's the case, then at some point, maybe tomorrow, maybe in 1 trillion years, a small region of space could quantum tunnel to the true vacuum state. This would create a bubble of true vacuum, expanding at the speed of light, converting false vacuum to true vacuum as it grows. Inside the bubble, the laws of physics would be different. Fundamental constants would have different values. Atoms as we know them couldn't exist. And the bubble would be unstoppable. Nothing could outrun it. Nothing could prevent it. Nothing could survive it. The universe as we know, it would simply cease to exist, replaced by a fundamentally different vacuum state incompatible with life, stars, or any structure. This scenario is called vacuum decay or false vacuum collapse, and the terrifying thing is that we wouldn't see it coming. The bubble would approach at the speed of light, so there would be no warning, no advance notice. One moment you'd be reading this script, and the next moment you wouldn't exist. The laws of physics themselves would change. Now, before you panic, let me emphasize that this is highly speculative. We have no evidence that our vacuum is false. Most physicists think it's probably stable. But the fact that it's even a possibility, that the fundamental nature of reality might be contingent, temporary, subject to sudden change, is deeply unsettling. It's a reminder that the universe doesn't owe us stability or permanence. But let's consider a more likely future, one grounded in what we actually observe. If dark energy is the cosmological constant and remains constant forever, the universe will continue accelerating, but not quite as dramatically as the Big Rip scenario. Instead, we get something called the Big Freeze or heat death. Here's how it unfolds. As the universe expands and accelerates, distant galaxies will recede from us faster and faster. Eventually, they'll cross the cosmic event horizon, the point beyond which they're receding faster than light. Not because they're moving through space faster than light, but because the space between us and them is expanding so rapidly that light from those galaxies can never reach us. Over billions of years, our cosmic horizon will shrink. Galaxies will disappear from view one by one, like ships sailing over the edge of the world. Eventually, only our local group of galaxies, the Milky Way, Andromeda, and a few dozen smaller galaxies gravitationally bound together, will remain visible. Everything else will have been carried beyond the horizon by the expansion of space. Future civilizations, if they exist, will look out at a universe containing only their local cluster, surrounded by infinite darkness. They won't be able to see the cosmic microwave background. They won't be able to detect distant supernova. They'll have no direct evidence that the universe had a beginning or that it's expanding. Most of what we know about cosmology will be impossible for them to discover. Think about that for a moment. We're living in a special time, cosmically speaking an era when the universe is old enough for intelligent life to emerge, but young enough that we can still see a rich, diverse cosmos. In the far future, the universe will be a lonelier place, and the beings living then, if any exist, will have a fundamentally impoverished view of reality compared to what we have now. But it gets worse. Not only will the observable universe shrink, but the stars will burn out. Star formation requires gas, and the gas in galaxies is gradually being used up, converted into stars, or locked up in stellar remnants. About 1 trillion years from now, the last stars will form. After that, no new stars will ignite. The universe will gradually grow darker as the existing stars exhaust their fuel. Small stars, red dwarfs, burn slowly and live long lives, potentially lasting for trillions of years. But even they will eventually die. And when they do, they'll leave behind white dwarfs, slowly cooling embers of once great stars. The universe will be filled with dead stars, black holes, and dark matter. Occasionally, a black hole might swallow a passing planet or star, briefly flaring to life. But these events will become rarer and rarer. And then there are the black holes themselves. For a long time, people thought black holes were eternal, that once something fell in, it was gone forever. But in 1974, Stephen Hawking discovered that black holes evaporate. They emit radiation, now called Hawking radiation, due to quantum effects near the event horizon. This radiation carries energy away from the black hole, causing it to slowly shrink. The evaporation rate depends on the black hole's size. Supermassive black holes, like the ones at the centers of galaxies, will take an unimaginably long time to evaporate. We're talking 10 to the power of 100 years. That's a googol years, a 1 followed by 100 zeros. But eventually, even they will evaporate, disappearing in a final burst of radiation. So here's the ultimate timeline. Stars burn out after 1 trillion years or so. White dwarfs cool to black dwarfs over 10 to the power of 15 years. Protons themselves might decay, disintegrating atoms over timescales of 10 to the power of 40 years. Black holes evaporate over 10 to the power of 100 years. And eventually, after timescales so long that they boggle the mind, the universe will reach a state of maximum entropy heat death. Nothing will happen anymore because there's no energy gradient to drive any process. The universe will be a uniform, cold, dark, empty void, expanding forever, with no structure, no change, no life. Time will lose all meaning because there will be no events by which to measure it. This is the heat death scenario, and it's arguably the most likely fate of the universe, given what we currently know. It's not a dramatic ending. It's a fade to black stretched over timescales that dwarf the current age of the universe by factors that have no human analogy. Now, you might be feeling a bit depressed right now, and I don't blame you. The ultimate fate of the universe sounds pretty bleak. But here's something to consider. All of these predictions assume that our current understanding of physics is complete and correct. And we know it isn't. We don't understand dark energy. We don't know if dark matter will reveal new physics. We haven't unified quantum mechanics and gravity. There could be phenomena, processes, or possibilities that we haven't imagined yet. Perhaps intelligence plays a role in the far future of the universe in ways we can't currently conceive. Perhaps there are ways to tap into the energy of dark matter, or to manipulate dark energy, or to create new universes. Perhaps the universe is cyclical, and the heat death is followed by a new Big Bang. Perhaps we're living in a multiverse, and life can migrate between universes as they age and die. I'm not saying these things are true. I'm saying that our predictions about the far future are necessarily limited by our current knowledge, and history suggests that reality is often more surprising than our theories anticipate. The universe has surprised us before. Dark energy itself is a perfect example, and it will likely surprise us again. But even if the heat death is inevitable, even if the universe is doomed to a cold, dark eternity, there's still something profound and beautiful about our current moment. We exist in an era when the universe is rich with structure, diversity, and complexity. Stars are shining, galaxies are forming, life is emerging. We are here, conscious and aware, able to contemplate the cosmos and our place in it. That's not nothing. That's not insignificant. The fact that the universe is mostly invisible, that its fate is determined by mysterious forces we barely understand, doesn't diminish the wonder of existence. If anything, it enhances it. We're fleeting patterns in a vast, dark cosmos, and yet we can understand, at least partially, the nature of that cosmos. We can map the invisible, probe the unknown, and push the boundaries of knowledge outward. Now, let me shift gears and talk about what the invisible universe means for how we understand reality itself, because this is where things get truly philosophical. The discovery that most of the universe is invisible challenges some deep assumptions we have about the nature of existence and knowledge. For most of human history, we assumed that reality was more or less what it appeared to be. Sure, there were things we couldn't see, atoms, molecules, distant stars, but these were hidden only by practical limitations, not by fundamental principles. Given the right instruments, we could see anything. The invisible universe challenges that assumption. Dark matter and dark energy don't just happen to be invisible to us right now with our current technology. They're invisible in principle. They don't interact with light. No matter how good our telescopes get, we'll never see dark matter in the conventional sense. We'll always have to infer its presence indirectly through its gravitational effects. This has profound implications. It means that direct observation, the gold standard of empirical science, has fundamental limits. There are components of reality that are forever beyond the reach of direct detection. We can only know them through their effects on things we can observe. Think about what this means epistemologically. How do we know something exists if we can't observe it directly? How confident can we be in the reality of dark matter and dark energy? These aren't idle philosophical questions. They get at the heart of how science works and what it means to have knowledge of the world. The answer, I think, is that science has always relied on inference, not just direct observation. We've never seen an atom directly, but we've accumulated overwhelming indirect evidence for their existence. We've never seen an electron, but the predictions of quantum mechanics that assume electrons exist are confirmed to extraordinary precision. Dark matter and dark energy are similar. We can't see them, but their effects are undeniable, consistent, and predictable. But there's something uniquely humbling about the invisible universe. It reminds us that reality is not obligated to be accessible to us. The universe wasn't designed for our comprehension. We're Johnny-come-latelys, evolved apes on a tiny planet, trying to make sense of a cosmos that vastly exceeds our intuitive grasp. The fact that we've made as much progress as we have is remarkable, but we shouldn't mistake that progress for completeness. Here's another implication. If most of the universe is invisible, what else might we be missing? Could there be other components of reality that we haven't detected yet? Not because they're technologically challenging, but because they don't interact with anything we can measure? Could there be entire domains of existence that are causally disconnected from what we call the universe? Some physicists have speculated about hidden sectors of particle physics, collections of particles that interact with each other, but not with normal matter except through gravity. Dark matter might be part of a hidden sector with its own rich physics that we can't probe because we're made of the wrong stuff. There could be dark atoms, dark chemistry, even dark stars, entire parallel structures invisible to us. This isn't science fiction. These are serious proposals being considered by particle physicists. The idea is that the visible sector the particles and forces we know about might be just one sector among many. The universe could be vastly more complex than we imagine, with most of that complexity forever hidden from us. Or consider the multiverse hypothesis. Some versions of inflation theory, the idea that the early universe underwent a period of exponential expansion, predict that inflation creates not just one universe, but infinitely many, each with potentially different physical constants, different particles, different laws of physics. These other universes would be causally disconnected from ours. We could never see them, never visit them, never directly confirm their existence. They would be invisible not just in practice, but in principle. Now, I want to be clear, the multiverse is speculative. It's not established science, like dark matter and dark energy. But it's taken seriously by many physicists because it emerges naturally from certain well-motivated theories. And it illustrates a broader point. The limits of the observable universe might not be the limits of reality. This raises a question. If something is forever unobservable, is it scientific to believe in it? This is where philosophy of science gets contentious. Some scientists, let's call them empiricists, say that science should only concern itself with what can be observed and tested. If dark matter particles are never detected, maybe we should abandon the hypothesis, even if it fits the data. If other universes can never be seen, maybe we shouldn't take them seriously, even if they're predicted by our theories. Other scientists, let's call them realists, say that science is about finding the best explanation for the phenomena we observe, and sometimes the best explanation involves things we can't directly see. Atoms were invisible for a long time, but believing in them was scientifically justified because they explained so much. Similarly, dark matter and even the multiverse might be justified if they're part of the best overall explanation for what we do observe. I lean toward realism, personally. I think reality is bigger than what we can measure, and our theories, when they're good, are telling us something true about that reality, even when they invoke unobservable entities. But I acknowledge that this is a philosophical stance, not a purely empirical one. Reasonable people can disagree. What's undeniable, though, is that the invisible universe has expanded our conception of what exists. It's humbled us. It's reminded us that the universe is under no obligation to make itself obvious to us. And it's opened up vast new territories for exploration, even if that exploration is indirect, inferential, and uncertain. Now let's bring this back to you, personally. Why should you care about the invisible universe? What does it mean for your life, your worldview, your place in the cosmos? Because this isn't just abstract cosmology. It has implications for how you understand yourself and your existence. First, consider the fact that you're made of rare stuff. Only 5% of the universe is normal matter, and you're composed of an even rarer subset elements heavier than hydrogen and helium, forged in the cores of stars and scattered by supernova. Every atom in your body was once inside a star. You're literally made of stardust, and not just any stardust, but the unusual, glowing, complex kind. But here's the twist. You only exist because of the invisible stuff. Without dark matter, galaxies wouldn't have formed. Without galaxies, stars wouldn't have ignited. Without stars, heavy elements wouldn't have been created. Without heavy elements, planets couldn't form. Without planets, life as we know it couldn't emerge. The invisible scaffolding of dark matter is what allowed the visible universe, your universe, to come into being. Think about that for a moment. You owe your existence to something you can't see, something you'll never directly interact with, something that vastly outweighs everything you can perceive. Your body, your planet, your solar system, your galaxy, all of it is a tiny luminous bubble floating in an ocean of dark matter. You're the rare exception, not the rule. And yet, you exist. Against all odds, the universe has arranged itself in such a way that atoms can become self-aware, can contemplate their own origins, can wonder about the invisible. Second, the invisible universe should instill a sense of humility. We tend to think we're pretty smart. We've figured out a lot about the universe. We have quantum mechanics, relativity, the standard model of particle physics. We've mapped the human genome, built computers, sent probes to other planets. It's easy to feel like we're close to a complete understanding of reality. But we're not even close. We don't know what 95% of the universe is made of. We don't know how to unify gravity with quantum mechanics. We don't know if there are other universes, other dimensions, other forms of existence beyond what we can observe. The invisible universe is a reminder that reality is vastly larger and stranger than our current theories capture. And that's okay. That's not a failure. That's the nature of knowledge. Every answer raises new questions. Every discovery reveals new mysteries. The more we learn, the more we realize how much we don't know. This should be exciting, not discouraging. It means there's always more to explore, always new frontiers to push toward. Third, the invisible universe challenges our sense of centrality. For a long time, humans believed we were at the center of everything. We were the pinnacle of creation, the most important beings in the cosmos. Then we discovered we're not at the center geographically. We're on a planet orbiting a star in the outskirts of a galaxy. Then we discovered we're not even made of the most common type of matter. We're made of the weird stuff, the minority constituent. This is the ultimate Copernican principle. Not only are we not at the center of the universe, but we're not even made of what most of the universe is made of. We're sidelined, marginalized, rendered cosmically insignificant by our own discoveries. And yet, we're the ones making those discoveries. We're the ones asking the questions, building the theories, probing the unknown. There's a paradox here. We're cosmically insignificant, and yet epistemically central. The universe doesn't care about us, doesn't revolve around us, didn't create us for any purpose. But we care about the universe. We're trying to understand it. In a very real sense, through us, the universe is trying to understand itself. We're the universe becoming self-aware, at least in this tiny corner of space and time. That's profound. That's meaningful. Not because the universe gave us meaning, but because we create meaning through our curiosity, our wonder, our relentless drive to understand. The invisible universe doesn't diminish that. If anything, it amplifies it. We're asking questions about things we can never see, will never touch, can barely imagine. And we're finding answers. Partial, tentative, uncertain answers, but answers nonetheless. Fourth, the invisible universe should expand your sense of possibility. If most of reality is invisible, if the universe is so much stranger than it appears, what else might be true that we haven't discovered yet? What other surprises await us? This is an invitation to intellectual humility and imaginative openness. Maybe consciousness is more fundamental than we think. Maybe life is more common. Maybe intelligence will persist far into the future, finding ways to survive that we can't currently conceive. Maybe there are forms of existence, modes of being, dimensions of reality that we haven't even thought to look for. The invisible universe teaches us that absence of evidence is not evidence of absence. Just because we can't see something doesn't mean it's not there. This cuts both ways, of course. It can lead to credulity, to believing in things without good reason. But it can also lead to openness, to being willing to consider possibilities that seem unlikely but aren't impossible. The key is to balance skepticism with wonder, to demand evidence while remaining open to surprise. Finally, the invisible universe should inspire a sense of responsibility. We're living in a brief, bright moment in cosmic history. We have the capacity to understand the universe, to explore its mysteries, to push back the darkness, both literal and metaphorical. That's a gift, and with it comes a responsibility to use it wisely. We should preserve and expand our knowledge. We should invest in science, in education, in the pursuit of understanding. We should cultivate curiosity in ourselves and in future generations. We should resist the forces intellectual, cultural, political that would suppress inquiry or limit exploration. Because the universe doesn't owe us anything, but we owe it to ourselves and to the cosmos to keep asking questions, keep seeking answers, keep pushing the boundaries of what we know. And we should remember that we're all in this together. Every human being is made of the same stardust, floating on the same pale blue dot, surrounded by the same dark ocean of invisible matter and energy. Our differences, nationality, ethnicity, ideology pale in comparison to what we share. We're all temporary arrangements of atoms, briefly conscious, trying to make sense of a universe that vastly exceeds our grasp. That should unite us, humble us, inspire us. So here's what I want you to take away from this. You are a rare and precious phenomenon in a dark universe. You're made of the glowing exception, the minority constituent, the stuff that can look up at the night sky and wonder. You exist because of invisible structures laid down in the early universe. Gravitational scaffolding you'll never see, but that made everything possible. You're living in a special time, when the universe is knowable, when curiosity can still be satisfied, when there are still stars in the sky and questions to ask. Don't waste it. Be curious. Ask questions. Seek understanding. And remember that the vast majority of what exists is invisible, unknown, waiting to be discovered. You're part of that story, part of that ongoing exploration. You're the universe waking up to itself, if only for a moment. Make it count. If that resonates with you, if you're feeling that sense of cosmic connection and responsibility, hit that subscribe button. And let me know in the comments, how has learning about the invisible universe changed your perspective? What question are you burning to explore next? Because we're not done yet. We have more to uncover, more mysteries to unpack, and I want you along for the journey. Now, let's dive even deeper into what the invisible universe reveals about the nature of reality itself, because we're about to explore some ideas that will genuinely bend your mind. We're going to talk about the holographic principle, the relationship between information and existence, and whether the universe might be fundamentally mathematical. One of the strangest ideas to emerge from modern physics is the holographic principle. This is the proposal that all the information contained within a volume of space can be described by information on the boundary of that space. In other words, the three-dimensional universe we experience might be a projection from a two-dimensional surface, like a hologram. This sounds like science fiction, but it comes from serious attempts to understand black holes and quantum gravity. In the 1970s, physicist Jacob Bekenstein discovered that the entropy of a black hole, the amount of information it contains, is proportional to the area of its event horizon, not its volume. This was shocking because usually entropy scales with volume. If you double the size of a container, you double its capacity to hold information. But for black holes, double the radius and you quadruple the area, hence quadruple the information capacity. This led physicists like Gerard 't Hooft and Leonard Susskind to propose that this might be a general principle. The maximum amount of information in any region of space is determined by its surface area, not its volume. The universe might be holographic, a three-dimensional projection of information encoded on a two-dimensional surface. If this is true, it has profound implications for the nature of reality. It means that the spatial dimension we experience might be emergent, not fundamental. Depth might be an illusion, a useful fiction that emerges from the underlying two-dimensional reality. You think you're living in three spatial dimensions, but the fundamental description of reality might involve only two. Now, why am I bringing this up in a discussion about the invisible universe? Because the holographic principle is intimately connected to the question of what's real and what's observable. If the universe is holographic, then there's a sense in which the real information is on the boundary, and everything we experience, the three-dimensional world, the objects within it, even our own bodies, is derived, secondary, projected. This resonates with the theme of invisibility. Just as dark matter and dark energy are invisible but fundamental, the two-dimensional boundary of the holographic universe would be invisible to us. We'd never directly experience it. We'd only ever see the three-dimensional projection. Reality would be, in a very real sense, hidden behind a veil of appearances. And here's where it gets even stranger. Some versions of the holographic principle suggest that the boundary is at the edge of the observable universe, the cosmic horizon, beyond which we can never see. All the information about everything that exists or could ever exist within our observable universe is encoded on that distant horizon. You, me, the Earth, the galaxies were all projections from that boundary. This is deeply counterintuitive, but it solves certain problems in quantum gravity. It provides a way to count the degrees of freedom in the universe, to understand black hole entropy, to potentially unify quantum mechanics and general relativity. The holographic principle is one of the leading candidates for a fundamental description of reality, even though it violates every intuition we have about how space works. Let me give you an analogy. Imagine you're playing a video game. You see a rich, three-dimensional world on your screen: mountains, forests, other characters. But all of that is generated from code stored on a hard drive. The code is one-dimensional, just a sequence of ones and zeros. Yet it gives rise to the three-dimensional experience. The holographic principle suggests something similar might be true for reality itself. The three-dimensional universe we experience is generated from two-dimensional information encoded on a cosmic boundary. Now, if reality is holographic, what does that mean for consciousness, for experience, for meaning? Are you just a pattern of information projected from a distant boundary? Does that make your experiences less real, less valuable? I'd argue it doesn't. Whether the universe is holographic or not, you still experience what you experience. Your thoughts, feelings, joys, and sorrows are real in the sense that they're part of the universe's actual state. The underlying description might be different from what you perceive, but that doesn't diminish the reality of your experience. It just means that reality has layers, depths, aspects that aren't immediately apparent. This brings us to another profound question. What is the relationship between information and physical reality? In classical physics, information was separate from matter and energy. Matter and energy were the real stuff, and information was just a description of that stuff. But in modern physics, especially quantum mechanics and thermodynamics, information has become more fundamental. The physicist John Archibald Wheeler famously proposed it from bit, the idea that physical reality emerges from information. Every it, every particle, every field, every aspect of the physical world comes from bits of information. In this view, information is not just a description of reality. It is reality. This is supported by several lines of evidence. Entropy, for instance, is fundamentally about information, specifically missing information. The second law of thermodynamics, which says entropy always increases, can be recast as a statement about information. The universe is constantly losing information about the details of its microstate. The arrow of time itself might be intimately connected to information and entropy. Similarly, quantum mechanics is fundamentally about information. A quantum state is a repository of information about the probabilities of different measurement outcomes. Quantum entanglement is about correlations in information. The act of measurement, which collapses the wave function, is fundamentally an information theoretic process. You're gaining information about the system, and that gain changes the system's state. Some physicists, like Seth Lloyd and Paul Davies, have proposed that the universe is literally a computer, processing information according to the laws of quantum mechanics. Every particle interaction is a computation. The universe is calculating its own evolution, and physical laws are the algorithm it's running. If this is true, if reality is information at its core, then the invisible universe takes on a new significance. Dark matter and dark energy might be information that's encoded in ways we can't easily access. They're part of the universe's computational state, but we can't read them directly. We can only infer their presence from how they affect the parts of the state we can read. This also raises questions about observation and existence. In quantum mechanics, what we observe depends on how we observe. The act of measurement affects the system. This has led some physicists and philosophers to propose that observation might be necessary for existence, that things don't have definite properties until they're measured. This is a controversial idea, and most physicists don't take it literally. But it points to a deep truth. Reality is not independent of how we interact with it. The universe we experience is shaped by our perspective, our instruments, our theories. The invisible universe is invisible, partly because we don't know how to look for it, don't have the right perspective or tools to bring it into view. Now, let's talk about one of the most provocative ideas in modern physics and philosophy, the mathematical universe hypothesis, proposed by cosmologist Max Tegmark. Tegmark argues that mathematical structures don't just describe the universe, they are the universe. Physical reality is a mathematical structure, and what we call the physical world is just our way of experiencing that structure from the inside. In this view, the laws of physics are not rules that govern matter and energy. They're descriptions of the relationships within a mathematical structure. Particles aren't little billiard balls. They're nodes in a mathematical network. Forces aren't pushes and pulls. They're transformations and symmetries within that structure. Everything that exists, from electrons to galaxies to consciousness itself, is a pattern within a vast mathematical object. This sounds abstract, but it has a certain elegance. Mathematics is, after all, unreasonably effective at describing the physical world. Eugene Wigner famously wrote about the unreasonable effectiveness of mathematics in the natural sciences, noting that mathematical theories often predict physical phenomena before they're observed. Why would that be, unless the universe is fundamentally mathematical? If the mathematical universe hypothesis is correct, then the invisible universe is just part of the mathematical structure that we haven't fully explored yet. Dark matter and dark energy are mathematical entities, particular patterns or relationships within the structure that we've partially identified but don't yet fully understand. Understanding them would be like solving a particularly difficult equation. We know the answer is there, encoded in the structure, but we haven't yet worked out all the steps. The hypothesis also suggests that all possible mathematical structures exist as universes. Our universe is just one structure among infinitely many. This is the ultimate multiverse, not just different regions of space with different properties, but entirely different mathematical structures, each as real as ours, each experiencing its own laws of physics, its own particles and forces. This is deeply strange and deeply beautiful. It means that every consistent mathematical structure is real, is a universe, is the home of patterns and possibly even conscious observers. It means that the question, why does anything exist, has a simple answer, because mathematical structures exist necessarily. You can't have non-existence of mathematical truths. 2 plus 2 equals 4 in every possible universe, including the null universe of nothingness. Now, I don't know if the mathematical universe hypothesis is true. It's speculative, and it raises more questions than it answers. But it's a serious proposal from a respected cosmologist, and it illustrates just how radical our understanding of reality might need to become to fully account for the universe we observe, including its invisible components. What all of these ideas, the holographic principle, the role of information, the mathematical universe hypothesis have in common is that they push us toward a view of reality that's fundamentally different from everyday experience. They suggest that the visible, tangible world is not the deepest level of reality. There are layers beneath, structures underneath, dimensions of existence that are hidden from direct experience, but are nonetheless fundamental. The invisible universe, in this context, is not just dark matter and dark energy. It's the underlying reality that gives rise to the visible world. It's the information on the holographic boundary, the mathematical structure, the quantum state. It's everything that's real, but not directly accessible to perception. And here's the thing, you're part of that hidden reality too. Your consciousness, your thoughts, your subjective experience, these are also part of the universe, but they're invisible to external observation. No one else can directly access your inner life. It's hidden, private, subjective, and yet it's real. It's part of the universe's actual state. This suggests a deep connection between the invisible aspects of the physical universe and the invisible aspects of consciousness. Both involve realities that are fundamental but not directly observable. Both require inference, modeling, indirect detection. Both challenge our assumptions about what exists and how we can know it. Some philosophers and scientists have even proposed that consciousness might be related to quantum processes or information integration in ways we don't yet understand. Roger Penrose and Stuart Hameroff have suggested that consciousness involves quantum coherence in microtubules within neurons. Others have proposed that consciousness is an emergent property of complex information processing, similar to how temperature emerges from molecular motion. I'm not going to claim that we understand consciousness, because we don't. It's arguably the biggest mystery in science, possibly even deeper than dark matter and dark energy. But I think there's a parallel worth noting. Just as we've discovered that most of the universe is invisible, we might need to accept that the most important aspects of existence, consciousness, meaning, subjective experience, are also invisible, accessible only from the inside. This brings me to a crucial point about knowledge and certainty. In science, we often talk about theories being proven or facts being established. But the invisible universe teaches us that certainty is elusive. We can be very confident about certain things, the existence of dark matter, the acceleration of the universe, but we're always working with models, approximations, theories that could be refined or replaced. This isn't a weakness of science, it's a strength. Science is self-correcting. When new evidence emerges, theories change. When better instruments become available, observations improve. The history of science is a history of surprises, of discoveries that overturned previous understanding, and the invisible universe is the latest, greatest surprise. But it won't be the last. There will be future discoveries that challenge our current theories. There will be phenomena we haven't yet observed, particles we haven't yet detected, forces we haven't yet identified. The universe is not obligated to be fully knowable, and we should expect that some mysteries will persist, that some questions will remain unanswered, possibly forever. And that's okay. That's part of what makes existence meaningful. If we knew everything, if the universe held no more secrets, what would there be to explore? What would drive us forward? Mystery is not the enemy of knowledge. It's the fuel for inquiry. The invisible universe is a gift, an invitation to keep searching, keep questioning, keep pushing the boundaries of understanding. So where does this leave you? You're a conscious being, made of rare matter, existing in a mostly invisible universe that might be holographic. Informational, mathematical, or all of the above. You're living in a brief moment of cosmic history when knowledge is possible, when questions can be asked and sometimes answered. You're part of a story that began with the Big Bang and will end. Well, we're not sure how it will end, but you're here now, aware, curious, capable of wonder. What should you do with that? I think the answer is simple. Be curious. Ask questions. Seek understanding. Marvel at the strangeness of existence. Connect with others who share that curiosity. And remember that the universe, for all its vastness and mystery, has given rise to you, a pattern capable of reflecting on its own origins, contemplating the cosmos, asking why. That's not insignificant. That's extraordinary. You're the universe experiencing itself, wondering about itself, trying to understand itself. The invisible components might be vast and dominant, but they're unconscious, unaware. You're the rare exception, the part of the universe that knows it exists. Cherish that. Protect it. Expand it. Because in a dark, cold, mostly invisible cosmos, consciousness is the light. And you're carrying that light, however briefly, however precariously. Make it count. Now, we're going to shift gears one more time and explore some of the practical implications of the invisible universe. Because this isn't just about abstract cosmology or philosophical musings. The search for dark matter and dark energy is driving technological innovation, shaping scientific careers, and potentially leading to discoveries that could transform our civilization. Let's talk about the experiments, the technology, and the potential breakthroughs that might finally reveal the invisible. The search for dark matter is one of the most ambitious scientific endeavors in history. Physicists have built detectors deep underground, launched satellites into space, and constructed enormous particle accelerators, all in the hope of catching a glimpse of these elusive particles. Let me walk you through some of the most exciting experiments currently underway. First, there are the direct detection experiments. These are designed to catch dark matter particles as they pass through Earth. The idea is simple. If dark matter particles interact with normal matter, even very weakly, and occasionally, one might collide with an atom in a detector. When that happens, the atom will recoil, releasing a tiny amount of energy that the detector can measure. The challenge is that these collisions are incredibly rare and produce very little energy. To have any hope of detecting them, you need three things: a very large detector to maximize the chance of a collision, exquisite sensitivity to detect the tiny recoil energy, and isolation from background noise. That's why these detectors are built deep underground, in mines or beneath mountains. The rock overhead shields the detector from cosmic rays, which would otherwise create too much background noise. The detectors themselves are also incredibly sophisticated. Experiments like XENON-1T and LUX use tanks of liquid xenon, cooled to extreme temperatures. When a particle interacts with a xenon atom, it produces a flash of light and a pulse of electrons, both of which can be detected. Other experiments use different target materials. CDMS uses crystals of germanium and silicon, cooled to near absolute zero. DMA uses crystals of sodium iodide. Each material has advantages and disadvantages, and by using multiple approaches, scientists hope to cover a range of possible dark matter properties. So far, these experiments have not definitively detected dark matter. There have been a few tantalizing signals DAMA has reported an annual modulation in their detection rate that could be consistent with dark matter, but other experiments haven't confirmed it. The Large Underground Xenon Experiment, LUX, and its successor, LZ, have set stringent upper limits on how strongly dark matter can interact with normal matter, ruling out some theoretical models. But the absence of detection doesn't mean failure. Every null result constrains the possibilities, narrowing down the parameter space where dark matter could hide. If dark matter interacts more weakly than current detectors can sense, we'll need even more sensitive instruments. The next generation of experiments, like XENONT and Darwin, will push the sensitivity even further. There's also the possibility that we're looking for the wrong thing. Maybe dark matter doesn't interact via the weak nuclear force at all. Maybe it's much lighter or much heavier than WIMPs. Maybe it's not a single type of particle, but a whole sector of dark particles with their own complex interactions. The field is adapting, exploring alternative candidates like axions and sterile neutrinos with dedicated experiments. Axion searches are particularly interesting. Axions, if they exist, would be extremely light particles that interact with electromagnetic fields under very specific conditions. Experiments like a DMX, the Axion Dark Matter Experiment, use powerful magnets and ultra-sensitive microwave detectors to look for the signal produced when axions convert into photons in a strong magnetic field. It's like trying to catch a whisper in a hurricane, but the technology is advancing rapidly. Then there's indirect detection. Instead of waiting for dark matter to hit a detector, these experiments look for the products of dark matter annihilation, or decay. If dark matter particles can annihilate with each other, turning into ordinary particles like photons or neutrinos, then regions with high dark matter density might produce an excess of these particles. The Fermi Gamma Ray Space Telescope has been scanning the sky for gamma rays that could come from dark matter annihilation. The IceCube Neutrino Observatory at the South Pole is looking for neutrinos from dark matter annihilation in the Sun or the center of the galaxy. So far, no convincing signals, but again, the search continues to constrain the possibilities. There's also the possibility of producing dark matter in particle accelerators. The Large Hadron Collider at CERN has been smashing protons together at enormous energies, and one of its goals is to create dark matter particles. If dark matter can be produced in collisions, it would immediately escape the detector without interacting, but we could infer its presence from missing energy and momentum. The LHC experiments ATLAS and CMS have been looking for these signatures. They found nothing definitive yet, but they've ruled out certain masses and interaction strengths for dark matter candidates. And the LHC is getting upgrades. The high luminosity LHC will collect much more data in the coming years, increasing the chances of a discovery. Now let's talk about dark energy. The experimental situation here is different because dark energy doesn't seem to be made of particles. It's more like a property of space itself. So instead of building detectors to catch dark energy particles, astronomers are mapping the expansion history of the universe in ever greater detail, hoping to understand dark energy's properties and evolution. Several major projects are underway. The Dark Energy Survey used a powerful camera on a telescope in Chile to map hundreds of millions of galaxies, measuring their positions, distances, and shapes. By studying how galaxies cluster and how their light is distorted by gravitational lensing, the survey has provided some of the best constraints yet on the nature of dark energy. The European Space Agency's Euclid mission, launched in 2023, is mapping the geometry of the universe and the formation of structure over cosmic time. It's observing billions of galaxies, measuring their redshifts and shapes, and using that information to probe dark energy. NASA's Nancy Grace Roman Space Telescope, scheduled to launch in the mid-2020s, will conduct even more detailed surveys. It will measure the expansion history using multiple techniques: supernova, galaxy clustering, and gravitational lensing. The hope is that by combining these approaches, we can determine whether dark energy is truly constant or whether it's changing over time. There are also ground-based projects like the Vera C. Rubin Observatory's Legacy Survey of Space and Time, LSST, which will survey the entire visible sky every few nights for 10 years. This will create an enormous dataset that can be used to study dark energy, dark matter, and a host of other phenomena. All of these experiments and surveys represent billions of dollars of investment and the work of thousands of scientists and engineers. They're pushing the limits of technology, requiring innovations in detector design, data analysis, and computational techniques. and they're training a new generation of scientists who will carry the search forward. But here's the exciting part. We might be on the verge of breakthroughs. The technology is advancing rapidly. Our theoretical understanding is deepening. And history suggests that when we push hard enough, when we look carefully enough, nature reveals its secrets. There's a real possibility that within your lifetime, maybe within the next decade, we'll detect dark matter particles directly. Or we'll discover something even more surprising that forces us to completely rethink our understanding of the universe. Imagine what that discovery would mean. It would be like Columbus reaching the New World, or Galileo turning his telescope to the heavens, or Watson and Crick deciphering the structure of DNA. It would open up an entirely new domain of reality, with implications we can barely imagine. New physics, new technologies, new understanding of how the universe works at its most fundamental level. And even if we don't make that discovery soon, the search itself is valuable. It's pushing the boundaries of what's possible. It's inspiring young people to pursue careers in science. It's demonstrating humanity's capacity for curiosity, perseverance, and collaboration across borders and cultures. The invisible universe is not just out there. It's in here, in our minds, in our theories, in our experiments. We're mapping it, probing it, slowly bringing it into the light of understanding. And you're part of that process. By learning about it, by caring about it, by supporting science and education, you're contributing to humanity's grand project of understanding reality. Now, before we move toward our conclusion, I want to take a moment to address a question you might be asking. Why should society invest so much in understanding the invisible universe? Why spend billions on particle detectors and space telescopes when there are so many pressing problems here on Earth? Poverty, disease, climate change? It's a fair question, and it deserves a thoughtful answer. First, the practical answer. Investment in fundamental science has historically yielded enormous returns. The technologies we use every day, computers, the internet, GPS, medical imaging, solar panels, all emerged from basic research that had no immediate practical application. Quantum mechanics was initially a purely theoretical inquiry into the nature of atoms. Now it underpins half the global economy. We don't know what technologies might emerge from understanding dark matter and dark energy, but history suggests there will be some. Maybe we'll discover new particles with useful properties. Maybe we'll learn to manipulate gravity or space-time. Maybe we'll uncover principles that lead to new forms of energy or computation. Or maybe the benefits will be more subtle, training skilled scientists and engineers, developing new technologies in the process of the search, inspiring innovation across fields. But there's a deeper answer too. Humans are curious by nature. We want to understand our place in the universe. That's not a luxury. It's part of what makes us human. We've been looking up at the night sky and asking questions for as long as we've existed. The search for the invisible universe is a continuation of that ancient quest. It's part of our cultural and intellectual heritage, as important as art, music, or literature. Moreover, the problems we face on Earth, climate change, resource depletion, the risk of conflict require global cooperation, long-term thinking, and technological innovation. The scientific enterprise, including the search for dark matter and dark energy, cultivates all of these. It brings together people from different nations and cultures in pursuit of common goals. It requires planning over decades, and it drives technological progress that can be applied to other challenges. I'm not saying we should prioritize cosmology over addressing immediate human needs, but I am saying that the search for understanding is valuable in itself, and it contributes to human flourishing in ways that aren't always quantifiable. A society that invests only in short-term practical needs and ignores fundamental questions about reality is a society that's lost something essential. Besides, the cost of fundamental science is often overstated. The entire annual budget of NASA is less than 1% of the U.S. federal budget, less than Americans spend on pizza each year. The Large Hadron Collider cost about the same as a single aircraft carrier. These are not budget-breaking expenditures. They're investments in knowledge, in capability, in our future. And there's something else worth considering: existential risk. We live in a time when humanity has the power to destroy itself through nuclear weapons, engineered pandemics, or environmental catastrophe. Long-term survival might require expanding beyond Earth, which requires advances in physics and engineering. Understanding the fundamental nature of the universe, including dark matter and dark energy, could be crucial to that survival. I'm not claiming that discovering dark matter will directly solve our problems, but I am claiming that a civilization that values knowledge, that invests in understanding reality, that maintains its curiosity and its capacity for wonder, that civilization is more likely to navigate the challenges ahead successfully than one that doesn't. All right, we've covered an enormous amount of ground. We've explored why most of the universe is invisible, what dark matter and dark energy are, or aren't, how we know they exist, what they mean for the fate of the cosmos, and how they challenge our understanding of reality itself. We've discussed the holographic principle, the role of information, and the experiments searching for dark matter. We've connected the invisible universe to consciousness, meaning, and your place in the cosmos. Now, let's bring it all together. Let's talk about what all of this means, why it matters, and where we go from here. Because this isn't just information I'm sharing with you. This is an invitation to a new way of seeing the world, a new relationship with reality. And I want to make sure you walk away from this with something meaningful, something that changes how you think about yourself and your existence. The invisible universe is, at its core, a story about humility and wonder. Humility because it reminds us that we don't have all the answers, that reality exceeds our grasp, that the universe is under no obligation to make sense to us. And wonder because despite all that, despite the vastness of what we don't know, we've still managed to learn so much, to map the invisible, to probe the unknown with remarkable success. Think about what we've accomplished. We've measured the composition of the universe to within a few percent. We've detected galaxies billions of light years away. We've traced the evolution of the cosmos from the first fraction of a second after the Big Bang to the present day. We've discovered that the universe is not just expanding but accelerating. We've inferred the existence of invisible matter and energy from their gravitational effects. We've built theories, dark matter, dark energy, general relativity, quantum mechanics, that fit the data with extraordinary precision. This is humanity at its best: curious, rigorous, collaborative, humble. We're asking the biggest questions imaginable and finding real answers, even if those answers raise new questions. That's not a failure. That's progress. That's what knowledge looks like. Not a final destination, but an ongoing journey. And you're part of that journey. Every time you ask a question about the universe, every time you marvel at the strangeness of existence, every time you seek to understand something beyond your immediate experience, you're participating in humanity's grand project of understanding reality. You don't need to be a physicist or an astronomer. You just need to be curious. But here's what I really want you to understand. The invisible universe isn't separate from you. You're not an outside observer looking at a cosmos that exists independently. You're part of the universe. You're made of atoms forged in stars, governed by the same laws that govern galaxies, existing within the same space-time that contains dark matter and dark energy. More than that, you're the part of the universe that's aware. Dark matter doesn't know it exists. Dark energy doesn't contemplate its own nature, but you do. You're conscious, self-aware, capable of reflection. And that makes you, in a very real sense, extraordinary. You're the universe waking up, looking at itself, asking why. That's not a poetic metaphor. That's literally true. The atoms in your brain, the neurons firing as you process this information, the thoughts and feelings you're experiencing right now, all of that is part of the universe's state, part of what exists, part of the story of cosmic evolution. Consciousness is not separate from the physical universe. It's an aspect of it, an emergent property of certain complex physical systems. You are the universe experiencing itself. And here's the profound implication. Your life matters. Not because the universe cares about you. It probably doesn't, at least not in any way we'd recognize, but because you care. You have values, desires, goals. You experience joy and suffering. You love and are loved. You create meaning through your choices and actions. And all of that is real, is valuable, is part of what it means to exist. The invisible universe doesn't diminish that. If anything, it enhances it. You're a rare, complex, improbable pattern in a vast, mostly dark cosmos. Your existence is contingent on countless prior events, the formation of the solar system, the emergence of life, the evolution of consciousness, the specific circumstances that led to your birth. You're the product of billions of years of cosmic evolution, and you won't last forever. You're temporary, fragile, finite. But that makes you precious, not meaningless. A diamond is valuable partly because it's rare. A sunset is beautiful, partly because it's fleeting. Your consciousness, your capacity for experience and understanding is valuable precisely because it's rare and temporary. Make the most of it. Cherish it. Use it well. This brings me to my final point, and it's about legacy. You won't live forever. None of us will. But the knowledge we gain, the understanding we achieve, the meaning we create, that can persist. It can be passed on to future generations, contributing to humanity's cumulative wisdom. When you learn about the invisible universe, when you grapple with dark matter and dark energy and the nature of reality, you're not just satisfying your own curiosity. You're participating in a conversation that spans generations, connecting you to the scientists and thinkers who came before and to those who will come after. You're part of a lineage of curiosity that stretches back to the first human who looked up at the night sky and wondered what those lights were. And you have a responsibility to that lineage, to preserve knowledge, to pass it on, to inspire curiosity in others, to resist ignorance, superstition, and anti-intellectualism, to defend science, education, and rational inquiry, to cultivate wonder in yourself and in those around you, because the alternative is darkness, not the darkness of the invisible universe, which is full of structure and complexity and mystery, but the darkness of ignorance, of willful blindness, of refusing to engage with reality. That darkness is spreading in some parts of the world. There are forces political, cultural, ideological that would have us retreat into tribalism, reject expertise, embrace comfortable lies over uncomfortable truths. We can't let that happen. We have to push back against that darkness with the light of knowledge, the warmth of curiosity, the fire of wonder. And that starts with individuals like you, choosing to learn, to question, to engage with the universe in all its strangeness and complexity. So here's my challenge to you. Don't let this be the end of your journey into the invisible universe. Keep learning. Read more about dark matter and dark energy. Follow the news from experiments like the LHC and the James Webb Space Telescope. Watch other videos, read books, take courses. Let your curiosity pull you forward into deeper understanding. And share what you learn. Talk to friends and family about the invisible universe. Inspire others with the wonder you feel. Support science education, whether through donations, volunteering, or simply encouraging young people to pursue STEM careers. Be an advocate for knowledge, a champion of curiosity, a defender of rational inquiry. Because the universe needs witnesses. It needs conscious beings who can look out at the stars, probe the invisible, ask the deep questions, and marvel at the answers. For billions of years, the universe existed without anyone to know it, to contemplate it, to care about it. And billions of years from now, when the stars have burned out and the universe has faded into darkness, there may be no one left to remember. But right now, in this brief, bright moment, you're here, conscious, aware, capable of wonder. You're the universe's way of knowing itself. Don't waste that gift. Embrace it. Celebrate it. Make it count. The cosmos is mostly invisible. Yes, most of what exists is hidden, mysterious, beyond our direct experience. But we're not blind. We have instruments. We have theories. We have intelligence and curiosity and determination. We can map the invisible, probe the unknown, push back the darkness. And in doing so, we create meaning. We find purpose. We participate in something larger than ourselves. You are a part of that. You matter. Your curiosity matters. Your wonder matters. Your life, brief and improbable as it is a contribution to the universe's story. The story of how unconscious matter became conscious, how ignorance became knowledge, how darkness became light. Thank you for taking this journey with me. Thank you for your time, your attention, your curiosity. If this has changed how you see yourself or the universe, if it sparked questions or inspired wonder, then I've succeeded. And if you want to continue this journey, if you want to keep exploring the mysteries of existence, hit that subscribe button. Stay curious. Keep asking questions. And remember, you're made of stardust, surrounded by dark matter, living in an accelerating universe, and you have the capacity to understand all of that. That's not nothing. That's everything. Until next time, keep looking up, keep wondering, and never stop asking why. The invisible universe is out there, waiting to be discovered. And you're part of the team that's going to discover it.